All right, ladies and gentlemen, so we're going to be diving on into the second half of 2.1 for this lesson, and we're going to start looking into what we call biconditional statements and one of my favorite things in our topic of logic and reasoning, which is truth tables. Okay, so the goals of this video are to be able to define and write biconditional statements and complete accurate truth tables. I'm keeping it the same with our success criteria. 4 things that you're going to have to be able to do to be successful within this lesson. 1, can you define what a biconditional statement is? 2, can you write your own biconditional statements, maybe given a definition first? 3, can you define what a truth table is? And then finally 4, complete a valid truth table for any logical statement. And obviously these are going to make a little more sense as we first dive in. So let's find out and take a look at what a biconditional statement actually is. So what we usually talk about when we talk about biconditional statements is the phrase if and only if. And a biconditional statement is a statement that contains the phrase if and only if. And the reason why is because it's kind of a statement that can go in either direction. So both the conditional and the converse of the statement are true. So we remember correctly that the conditional statement is if P, then Q. And the converse of that statement should be if Q, then P, right? So we just switch them out a little bit. Let me show you what I mean. So let's say we know our conditional statement goes P implies Q. And then our converse would be Q implies P. And so a biconditional statement happens when both P implies Q is a true statement and Q implies P is also a true statement. You can see our symbolism in here, the P if and only if Q. The symbols is the double-sided arrow, again, kind of recognizing that P implies Q is true, and Q implies P is also true. So what we're going to start looking at biconditional statements is, now here's the definition. Let's see if we can kind of take some other definitions or statements and see if we can actually go ahead and create our own biconditional statements based off of a definition. So the definition that we see in example number 1, and as you're going through this video, of course, pause the video anytime that you need to write down some of the definitions or to take some more accurate and proper notes. Obviously, once you pause it, I'm not going anywhere. I'll be right back. So, definition. If 2 lines intersect to form a right angle, then they are perpendicular lines. So we're going to use this definition to turn this if-then conditional statement into a biconditional statement. So a great way to start off with is to first identify the definition. Well, that's already been given to us, so we're good there. And then the second thing would be to identify what the actual converse is. So the converse, remember guys, is just to switch the following. So the converse of this particular example would be if 2 lines are perpendicular, then they are right angles, right? Or then they form, or then they intersect to form a right angle. Keep it consistent, all right? Then they intersect to form a right angle. All right, so that is the converse. So what our goals are is we want to kind of utilize both the definition and the converse to put it into a if and only if statement. So in an example like this, we kind of use the truth value of both of them to write the biconditional. And so, well, we have to write it in a sense where both ways are true. So how about we talk about the lines forming a right angle first and foremost. 2 lines intersect to form a right angle. Now, our goal is to now think about, well, what is the possibility for 2 lines to intersect and form a right angle? Well, what is true about those lines? Well, we've already discussed that if they're going to form a right angle, they have to be perpendicular to one another. So, if and only if the two lines are perpendicular. So that's how we would make our biconditional statement. Now you could have gone in the other direction. You could have said if two lines are perpendicular, or should we say two lines are perpendicular if and only if the two lines intersect to form a right angle. So it's true in both cases. I read basically from left to right, or I can read from right to left, switching, and it'll be the same. Now, while we're on the topic of biconditionals, let me talk a little bit about notation. If you ever see IFF, that stands for if and only if. Okay, so a lot of times we will abbreviate if and only if for IFF. So just kind of be on the lookout for things like that of the nature. Okay, so recap. Find the definition, write the converse, and then kind of utilize the definition and the converse together to make a statement in which the first one only happens if the second is true. And it can go in reverse order. The second is true only if the first is true. Let's take a look. Give this one a shot on your own. I encourage you to pause the video right now, give this one a shot, and see where you go. Let's take a look. Definition. If an angle is a right angle, then its measure is 90 degrees. We know it's a true statement. Its converse, in this particular example, would say, hey, if an angle is 90 degrees, or if the measure of an angle is 90 degrees, all right, if the measure of an angle is 90 degrees, then it is a right angle, right? So we just switched the Q and the P, hypothesis and the conclusion. So that would make our biconditional a combination of utilizing them. So how about this? An angle is a right angle if and only if the measure is 90 degrees. And now your wording might be a little bit different, than what I'm typing exactly on out here, and that's okay. They're not going to be exact word for word, letter for letter, but the concept has to be the same to understand that, hey, an angle is a right angle if and only if the measure is 90 degrees, or if the measure is 90 degrees, then it's a right angle. So it goes both ways. All right, so it goes in both examples. Let's try one more of a real life example here. Again, I challenge you to go ahead and to pause the video, see if you can make the biconditional on your own before we go over it. So the original statement says, if you can run for president, then you are at least 35 years old. If you are at least 35 years old, then you can run for president. Okay? So we're putting things all together. So if you can run for president, then you are at least 35 years old. If you're at least 35 years old, then you can run for president. So it's almost like here, the very first part is our definition. Our second sentence is our converse, and our goal is to combine the two. The first one will act as our conditional statement. The second sentence, starting with if you are at least, will act as our converse statement. So putting them together, what's the only way you can run for president? You can run for president if and only if you are at least 35 years old. I hope that makes sense, guys, because it's true. Like, if you are 35 years old if and only if you're running for president. It's kind of an awkward statement to say, but it's true as well, right? So there's kind of a way to utilize it in a real life example. So hopefully biconditionals aren't too much of a challenge for us as we dive on into our next topic of this video, which is to look into truth tables. Now, as you can see by the kind of top of this slide, I love truth tables. They're so fun to me. It is so much it's interesting to work on the logic, to figure out what happens when things imply other things, what happens when things are including other things, when they're not including other things, when they're negating things. I absolutely love them. And this is where it all starts, is the actual conditional statement truth table. All right, let's look into it. What is it? What does it look like? What are all these things in here? Let's find out. Well, we already know P is our hypothesis, Q is our conclusion, so our conditional statement is if P, then Q. Okay, so then we ask ourselves, what is the truth value of the statement? Okay, what is the truth value of the statement? So what we're asking ourselves is, if blank, then blank. Is that a true statement or a false statement? That's where our conditional, our truth tables come on into play. All right, so it's if you like colors, then you like the color blue. That's a true statement, because if you like colors, then you do like the color blue. But then you could say maybe the reverse isn't always true. All right, if you like blue, then you like colors. Well, maybe, but not all the time, right? It might not always be true. So where does it stem from? There's 4 options for P and Q. The hypothesis could be true, and the conclusion could be true. The hypothesis could be true, the conclusion could be false. The hypothesis could be false, the conclusion could be true, or they both could be false. And now it's our job to figure out what happens when you get a true implies true, a true implies false, a false implies true, and a false implies false. So let's see what happens. When you have a true hypothesis and you finish with a true conclusion, that means your entire conditional statement is going to be true. All right. What happens if you have a true hypothesis, but then you end up with a conclusion that we just know is false? Okay. So if we have a true hypothesis, like you're thinking something is about to happen and you know it is true, but then some experiment goes on and the conclusion of this experiment actually gives you a false result in the end. Well, that's the case when it's false. And you're going to come to find out it's the only case in a conditional statement when it's false. What happens if it's false implies true? Well, think about it. Think back to like chemistry classes, or biology for that matter. You're working on a science experiment, and you make a hypothesis. And the hypothesis, or the good estimate guess that you make, all right, ends up being false. You do the science experiment, and even though you may have debunked your actual hypothesis, you still found a conclusion that was true. So if that's the case, it's a true statement overall. Okay. Our last one, what about when we have false implies false? Now, most students immediately say, well, false and false, it's like, gotta be false, right? Wrong. Because think about it. If you take a prediction that is false, you do some experiment that also results in something false, then together they must make a true. It almost kind of reminds me sometimes of like when you take a negative times a negative, well, it's going to be a positive, right? Now, that's not exactly how it is, but it's got some kind of, significance in relation. So this conditional truth table here is where you're going to start for everything. You have to know that true gives us true. True, false gives us false. False, true gives us true. and false, false gives us true. These are the stepping stones and the backbone for our entire truth table discussion. So let's take a look at when it's not always P implies Q. What happens if we look at the converse, inverse, or contrapositive? So all of your truth tables should start off like this. P, Q, and your four scenarios. True, 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 false, false, true, and false, false. These first two columns should never change. It should always be the exact same. Well, why is that? It's because it's the only four scenarios that can ever happen in P and Q, right? There's only there's only one hypothesis and one conclusion. There's only four outcomes that could possibly be the case. Well, we know the converse is to switch Q and P. So follow my marker as I go through this video. I am now not following P implies Q. Now I am following Q implies P. So you should be looking not from left to right, but instead right to left. So true implies true is still a true statement. Still a true statement. False implies true. Well, false to true was a true statement in conditional, and it is true in converse because I go from Q to P now. All right, stay with me. From true to finish in false, that was the only time when we had a false statement. And then lastly, false implies false is still going to be a true statement. Now I hope that makes sense, because as you see in the tables for the inverse and the contrapositive, they are much bigger. There are more columns in our two inverse and contrapositives, and there will be more than just these three columns that we have here. Because think about it, what it means to be the inverse. If you remember correctly, the inverse meant you had to negate P and negate Q. So the inverse is not P implies not Q. So when we're dealing with truth tables, ladies and gentlemen, this is the kind of the clue for us is you have to have a column for every part of the truth table. Let me say that one more time. You have to have a column for every part of the truth table. So P and Q remain the same. If you look at your end statement, not P implies not Q, you see that there is a not P and you see that there is a not Q involved. You have to include those in the truth columns. Before I can make a statement about not P implies not Q, I have to actually find out what not P and what not Q actually is. So let's go ahead and do that. Not P, so not true is false. Not Q means not true is false. So really, we have false implies false, which is true. Let's keep moving. Again, at any time, if you need to slow down and replay the video, by all means, go ahead. Again, let's go down here. I need to know what not P is before I can do anything with my truth value statement. So not true is false. Not false is true. So now we have false implies true still gave us a true statement because true was second. All right, what about not P and not Q for row 3? Well, not false is true, not true is false, and false and true give us a false, or I should say it the other way. True and false give us false. True implies false is a false statement. Remember, if false comes second in the implication statement, it is going to be false. All right, and so then we have not P and not Q for false. Not false is true. Not false is true. So true implies true is still a true statement. All right. I challenge you at this time to do the contrapositive on your own. Remember what the contrapositive is though. Not Q implies not P. So you need to go ahead and to find out, first and foremost, what all the not Q's are, what all the not P's are, and then do not Q implies not P. Pause the video, see if you can do it on your own. Let's see how you did. True becomes false, true becomes false. So false implies false is a true statement. True becomes false, false becomes true. So now Q, not P should be true, implies false, which when false is second, it is a false statement overall. For row 3, not Q becomes false, not P becomes true. So I'm looking at false implies true, false implies true is a true statement. And last but not least, false becomes true, false becomes true, true implies true is a true statement. I know it seems like a lot and you're like, oh my gosh, all he's been saying is true and false for the last 5 minutes. I have, but I'm telling you guys, it's logical, it's thought-provoking, it's going to really get you kind of more understanding on truth and debate and how to put up valid arguments. There's a lot that goes along with our truth tables and as we continue to go into some geometric proof. So as we close up this particular video, we're going to look on into a couple more symbols, all right, a couple more symbols and one last truth table. So the symbol you see here is a caret, all right? The caret that we're looking at, all right, is kind of that in between P and not Q, okay? So this is the symbol, if I can draw better, this is the symbol for and. If you see it turned over, it is the symbol for or. And of course, we know our negation as not. Okay? All right. So what is and what is or? Well, think about it. When you include and in a statement, you're not leaving any room for kind of, or kind of, sorta, or either or. When you say this and that, for the statement to be true, both this and that have to be true. If I'm going to make the entire statement be true. But when I'm talking about an or statement, only one of them needs to be true. Because if you're asking if the statement this or that, either this or that have to be true to become a true overall statement. So let's look at a truth table here real quick. And definitely feel free to pause the video, take a challenge for yourself before we dive on in to see what we need here. But first and foremost, we know that we need to start with P and we need to start with Q. Well, now we got to figure out what else is in our truth table. Well, there's a not Q in the truth table we're going to have to know. Inside of those parentheses is a P and not Q. And then the entire statement is a not P, not, or and, excuse me, not Q. Let me say that one more time so we don't get confused. that is a not, parentheses, P and not Q. So what this means, guys, when you see the parentheses, is the entire parentheses will have a truth value, and then we will negate it, take the complete opposite. And that's what we did in this fourth column right here. Let's take a look. We're going to have some fun with this one. All right. So it's our same thing that we've been doing. True, 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 false. We have false, true, and false, false. So those are our four options. So let's first and foremost identify what not Q is in all of them. Well, a not true would be false. A not false would be true. A not true would be false. A not false would be true. Still with me? Good. Look in the fourth column. P and not Q. So for this statement to be true, both P and not Q have to be true. Let's take a look. True and false. That is a false statement. That is not like our implications. It is not P implies not Q. It is P and not Q. Let's go to the next one. True and true. That's a true statement. Both of them are true. False and false. That's a false statement. Be careful. This is not an implies statement. This is an and. So the only way for an and to be true is true and true. Our last one, false and true, one of them is false. That means that it is false. So be careful, especially on a false and false example, because that is a false result, not a true implication like it was in our previous truth tables. And now we will finish up with the last column where we negate the entire statement in the fourth column. So this whole fourth column, just negate it. The opposite of false is true. The opposite of true is false. False becomes true. False becomes true. Okay? And that, ladies and gentlemen, is a complete truth table for our statement, not P and not Q. All right, ladies and gentlemen, hope you had as much fun as I did. Love my truth tables. Keep practicing them. If you had some trouble, I highly recommend going back through the video, pausing, so you can try them on your own and see what you rise at. Have a good one, folks. Till the next one.